Hi, we're going to go over graphing rational functions, and today we're just going to go over something called an asymptote. So first of all, what is a rational function? Well, a rational function is one that looks like a fraction. Your book describes it as p of x over q of x. The important thing is that the denominator, the q of x, has to have an x value in it. So the other issue is that q of x, our denominator, cannot equal 0. Some examples of some rational functions are shown here. The most basic rational function is 1 over x. Then you have a little more complicated ones, x plus 1 over 2x squared plus 5x minus 3, and the 3x squared minus 3x minus 6 all over x squared plus 8x plus 16. Something to keep in mind when you're working with rational functions is that you really do need to think about factoring. That's important when we're working with rational functions. Another thing to keep in mind is that our denominators cannot equal 0. So that's one of the important parts or characteristics of a graph is what value of x makes that denominator 0. Here's that basic function that I mentioned, 1 over x. And on the left-hand side of the screen, if you choose various values for x, you get certain values for y. And that's how you can come up with this graph here. This graph is known as a hyperbola. And all rational functions are going to be some type of hyperbola. Now, this asymptote that's mentioned here, vertical asymptote, that's like an imaginary line that our graph does not cross. Our horizontal asymptote, another imaginary line that our graph usually does not cross. For some reason, graphs never ever cross vertical asymptotes, but they can sometimes cross horizontal asymptotes. You see your domain and your range up here. So our domain goes from negative infinity all the way up to the y-axis, so all the way up to an x value of 0, but it doesn't include the x value of 0. And that's why we have to have our domain and our range into two separate chunks. A range starts at negative infinity and travels up to the x-axis and has to stop, and then it continues again, starting at 0, on up to positive infinity. They use the term discontinuous, meaning our graph has a break in it. When x is 0, our graph has a break in it, and that's a characteristic of these rational functions. Here's a picture of the graph of y equals negative 2 over x. So if we just pick some values for x and see what they give us values for y, then we can see we'll get a rational function, a hyperbola, and it's got a horizontal asymptote of the x-axis and a vertical asymptote of the y-axis, which helps us find our domain from negative infinity to 0 and 0 to infinity, and also our range, which turns out to be the same thing. Now here's another rational function. This one's called the reciprocal function, 1 over x squared. And it's a hyperbola, but it's not quite the same type of hyperbola that we saw before. It does have the same domain as it did because it exists out here at negative infinity as we travel on the x-axis, and we have to stop at 0 like we did before. Then we can pick up our graph again after we cross over our y-axis and continue on. However, the range is different. There is no graph under the x-axis, so there are no y values that are negative. So our range is strictly from 0 to infinity. Now, how do we go about graphing these? Well, these are 5 important pieces to graphing a rational function. We need to find out what our vertical asymptotes are, what our horizontal asymptotes, our x and y intercepts, which are very similar to how we found them in other graphs, and then we'll have to pick some test points to fill in the rest of the graph. So all I'm going to do today is show you the vertical asymptote. And by the way, here's the rest of the graph over here. So I've got a vertical asymptote here in red, a horizontal asymptote in blue, a y-intercept in green, and test points to fill in the rest of the graph.